Hi everyone, I'm Miao from University of California, Los Angeles, and today I will present our paper, Multi-Level Interconnect Planning for Signal, Power, and Thermal Integrity in 2.5D and 3D Integration. So here are the main content. I will start with the background and the motivation. So what are chiplets? Well, a chiplet is a small chip that contains a well-defined subset of functionality, which is usually partitioned from a monolithic chip. And the chiplets are usually integrated with advanced packaging technologies, such as 2.5D and 3D, as shown in the figure 1 here. Well, we can see a lot of interconnects in these packaging forms, such as the microbump, the vias and segments in the IDL layers, and the through-silicon vias, the TSV, as well as CFL bumps, TPV, and EVA. So we divide these interconnects into two categories, that is the vertical interconnects, including bumps and vias, as well as planar interconnects, including the wires in the interposer IDL and the planes in the substrate IDL. So then we will see how these interconnects influence SI, PI, and TI, which are the key metrics of the chip. So for die-to-die signal integrity, so the SI is signal integrity, which describes the quality of signal transmission. And for die-to-die signal integrity, there is usually a large number of parallel transmission lines. For example, in modern memories, such as HBM. And we need to add ground guiding tracks to form a GSG or GSSG pattern. And maybe we can add a lot of, not a lot of, but several signal wires between two ground guiding tracks. And we can see in figure 2A here that, we can see in figure 2A here that as we put more signal wires between two ground wires, the insertion loss gets worse. And for DCPI, we want to say that the interconnects are considered as a resistive network whose resistance is determined by the density and geometric shape of these interconnects. And a quick example is that as we increase the VI pitch on the silicon interposer, we can see the maximum IR drop severely increase. It's easy to understand because we increase the VI pitch, we decrease the number of vias per unit area, and we increase the resistance. So a simple approach is to, well, we can add more vias in it, right? But the problem is it consumes dotty resources, and it causes higher manufacture cost. Also for TI, we want to say that the vertical connects can form heat transfer channels and become hotspots. Okay. So realizing the importance of the interconnect, we want to do the planning in the early stage. There are two main challenges in the interconnect planning. The first is that the design space is too large. We consider 15 dimensions in total, and which will result in 25 billion combinations. And it is impossible to exhaust all the combinations by doing 25 billion physical simulations. Also, the design rules in the interposer and substrate are distinct, so we cannot directly transfer the optimization strategy on one thing to another. And the second challenge is that the multi-physics criterions and the probability constraints are coupled, and this coupling introduces nonlinearities in our planning and optimization problem, and bring difficulties for solving this problem. And in this work, we do quantitative SI, PI, and TI analysis, which is different from previous works. Okay, so here is our framework for optimizing the interconnects. It is called the MIP-SPT. And we actually use a multi-phase Bayesian optimization framework. Let's go to the details. So considering an optimization problem, we first look at the objective and constraints. So our objective is to minimize the cost of interconnect manufacturing. And the constraints include SI, PI, and TI. We consider the insertion loss, the maximum IR drop, as well as the maximum temperature. Also, we want to make sure that the chiplets are routable, so we will not occupy too much routing resources. Then let's go to one of our key strategies, that is the hierarchical variable scheduling strategy. In this strategy, we divide the parameters into different phases and optimize them accordingly. Well, in phase 1, we optimize the interposer, while the parameters of the interposer and signal bump. And in phase 2, we do signal bump and substrate. Well, we optimize the signal bump in both stages because, well, it is a bridge between the interposer and substrate. And in phase 3, we optimize all variables based on the information from phase 1 and phase 2. So here is the physical logic behind our hierarchical scheduling. So first, for SI, well, the die-to-die signal connections in chiplet integration are routed on the interposer and are mostly irrelevant to the substrate. And for PI, we can decompose the package PDN into two cascaded subnetworks. And the total IR drop is roughly the summation of that is the interposer and substrate. Of course, it is not strictly the same, but roughly the same. So we can, to some extent, divide the parameters into different phases. And for TI, similar to PI, if we consider the overall thermal resistance, it can also be approximated as a series combination of the interposer and substrate components. And another thing we do in our optimization framework is a candidate selection strategy. Actually, we have too many points in that space, even after our hierarchical variable scheduling. So we just want to select the most promising candidates for acquisition function. Otherwise, we will the runtime will explode. So we adopt different technologies in different phases. In phase 1 and phase 2, we do multi-score down selection, and in phase 3, we add an elite bias sampling. So the multi-score down selection, we have 3 scores. That is the exploitation score that exploits the physical regions for high objective values, and an exploration score that explores the uncertain yet promising regions, as well as a boundary learning score, which selects points near the boundary of a physical region and helps the convergence of our algorithm. And we use a random selection as a fallback. I will not go into the details of these formulas, and because of limit of time. And we still have too many points in phase 3, because remember, in phase 3, we optimize all the parameters. So fortunately, we have historical good visible points obtained from phase 1 and phase 2 because of elites. And we just concentrate around the elites and sparsely sample the rest of the space. So we do this elite bias sampling, and the probability of selecting one point is constituted by 2 parts. The first is how close it is to an elite, and the second part is the uniform selection. Okay, this is a quick evaluation study of our candidate selection. We achieve our multi-score down selection achieve 38 times speed up on average in phase 1 and phase 2, and our elite bias sampling achieve an additional 7.8 times speed up in phase 3. And we will show in the experiment that this speed up will not influence the final convergence or optimization results of our algorithm. Okay, the last thing we do in our optimization framework is a trick we do in the acquisition function. So first, I will introduce how we select the acquisition function. At the beginning, when we only have a few physical points, we want to quickly accumulate the number of physical points so we can fit the Gaussian process model. So we use the probability of feasibility plus the log QF to, as the acquisition function. And in normal cases, we just use the commonly used expression improvement, log EI. But one thing we do here is that we tune the constraint stringency in our acquisition function. So our constraints, SI, PI, and TI constraints, are considered as a multiplicative weight in our acquisition function, as shown in this formula. And we use a hyperparameter eta to control the softness. So eta is determined by our recent feasible rate, R, which means like how many points are feasible in recent trials. For example, we have 6 out of 10 points that are feasible in the most recent 10 trials. So if we have a large R, it means we may be too conservative, we can increase eta and we get a softer constraints. And if we have a small R, we might be too adventurous and we might not be able to get enough, we might not be able to get a lot of feasible points. So we just decrease eta and we get harder constraints, which means the points will be more feasible. Okay, so let's move to the experiment part. We experiment on the MQQ architecture and on 2.5D cases and 1.3D cases. So, and the phase structure parameters which are not optimized are listed below. And for the SI, PI, and TI constraints, we have several combinations. And here is a comparison between our multi-phase Bayesian optimization and the baseline single-phase BO. So the baseline is that we simply put all the parameters into a Bayesian optimization framework. And we can see that we achieve better convergency and better optimization value in all 8 cases. And then we provide a quantitative comparison. So we can see we achieve like 24.12% improvement in the convergence value, while the standard deviation is only 0.53%, which means we get better optimization results and the optimization procedure is more stable. And we also reproduce and compare with previous works. And on average, we reduce the manufacturing cost of the interconnects by 23.1% and 18.1% respectively. And such advantage comes from the effective exploration of the data space and the careful treatment of physical constraints. And that's all for the presentation. And I think it's time for some questions.
Great. Thank you very much. We've got time for a few questions. We managed to tighten it up.
Thank you for your very interesting talk. My question is, you consider about SI, PI, and TI. Why don't you consider like stress? Because stress is more important for the 3D and the 2.5D integration. Yes, this is my first question.
Yes, we haven't considered the stress because first in this work we want to consider more about electrical metrics instead of the physical metrics. And also for stress, I think we have a lot of things that influence the stress of the 2.5D and 3D integration. So we haven't clearly figured out the mechanism of interconnects that influencing the stress problem. So that is also in our future work because our group is also developing the simulators for stress simulation for 2.5D and 3D integration, and we hope we can do that in the future planning of the interconnects.
Okay. Relation is you consider so many different evaluation metrics, and do you have any priority about the SI, PI, and TI? Which evaluation metrics do you prefer?
Yes, actually, in this work, the dominating matrix is the PI, power integrity. While for SI and TI, we just want to, we want to make sure that they obey the constraints. They will not violate the constraints. That's enough, and that is not hard to guarantee. But for PI, you can also see in our experiment we have 4 maximum IR drop constraints. We experiment 4 combinations. So in this work, the PI is the dominating constraint we want to address.
Okay, thank
Yeah, thank you.
You have more questions? I had one. So it's 24% manufacturing cost. How are you dividing that up? There's a cost of making the dies. There's a whole sorts of 24% of how much?
Actually, 24% is not manufacturing the die. Actually, it is manufacturing just for the interconnects.
Just the interconnect.
Yeah, because we cannot have a complete model for the die cost problem. It is so complicated.
Right. That's sort of the. It's an interesting. I mean, it's a good improvement on that chunk of it, and sort of in the big picture, how much impact. Interesting.
Yeah. Thank
Do
you.
we have more questions? We've made. Yeah.
Could you hear anything I said?
Yeah.
So I was wondering if by selecting a few points to reduce the size of the problem, you end up making the Bayesian optimization problem much harder because maybe you fragment your search space.
Sorry, I cannot hear you very clearly. Yeah.
So you have a large optimization problem,
Yeah.
and to simplify it,
Yeah.
you select a few promising points.
Yes.
By doing that, I wondered if you make the problem harder because maybe you fragment your parameter space.
You mean, yes, I just select several event points to make this problem easier. But actually, that is only phase 3. And phase 3 is just a fallback. So theoretically, we can finish the optimization after phase 2. And in phase 1, phase 2, and over, and it's done. But in phase 3, we just want to make sure that we do not fall into the local optima, and we do phase 3. We select some edit points and do some optimization. But phase 3 is not the key component of our framework. Yeah. And actually, another approach is to iteratively do phase 1 and phase 2. But that will cost a lot of time. And according to our experiment, the phase 3 can replace the process of iteration, and we just do that.
Okay. Very good. Any other questions? Oh.
Maybe I missed it, but what technology are you targeting? Because as we go 3D, we use a lot of backside. And I wonder how relevant is what you are proposing here for backside power delivery, especially going 3D.
Thank you for your question. And in this work, we did not do backside PDN or backside power supply. Actually, we mainly work on the interconnects in the interposer. I think in the interposer, we use a relatively, not so advanced technology on the interposer. And for a problem of backside PDN, if you go to the very beginning of this presentation, you can see our modeling for 2.5D and 3D integration. It is not. Yeah, we do not adopt the most advanced technology such as backside PDN. Yeah. But I think this approach can be extended to backside PDN as long as we know like for example, the wire width, the spacing, the via pitch, and the via diameter. If you know these structural parameters, I think it is easy to extend to backside PDN.
All right, I think we're pretty close to time, and we